Good afternoon to all. I am Beerbal Solanki, Assistant Professor in Akgec College, Ghaziabad. Today we will discuss the topic that is regular expression, and deeply we define the topic that is how to write the epsilon NFA from the regular expression, that is the conversion of the uh, regular expression into the epsilon NFA and NFA. And other topic is that closure property of the regular language, and also the other topic is decision property of the regular language. So we define one by one. That topic is the regular expression to NFA. NFA, that is the non-deterministic finite automata. So we write the epsilon NFA and NFA for the given regular expression. So the first question is that construct the NFA from the given regular expression A, clean closure of A and clean closure of B and clean closure of C. So how to write the uh, NFA from the given regular expression? So here Q naught is a initial state. Q naught is the initial state, and take the input as A, here BC A, and epsilon, and then Q1 state, and the clean closure of B. So we write the self loop for that, and also the self loop for A, because A is a clean closure, and epsilon and Q2 is a final state, and C, the clean closure of C. So we can write the self loop for that also. So this is the epsilon NFA for the given regular expression. Now we write the regular expression for the another regular expression. So the question can be as write the epsilon NFA and NFA for the given regular expression, that is the regular expression is A, bracket A plus B, clean closure and concrete B. So we write the regular expression for that. We start the string from the starting variable, that is A. So we write from the initial state. Q naught is a initial state. Input is A, and input is A. We give the input A to reach the Q1 state. Now A plus B is the clean closure, so we write the epsilon, and input can be A or B. So it can be write A comma B. This is self loop because it A plus B is the clean closure form. Now epsilon, here this is the rule for clean closure, epsilon and self loop for the clean closure. This is for the variable, and we reach the Q3 state if we give the epsilon input, and now here B is also the input in the concurrent form, this. So we write the A's as, and Q4 is the final state, because here the string is finished. So it is the final state. Now this is how to convert this in this form. So A bracket A plus B clean closure B. So if we write the A here, A इनपुट यहाँ से लिया आपने, देन इसके बाद आपके पास चॉइस है या तो A लें या B लें या फिर इसमें से कुछ लें। एप्सिलॉन भी हो सकती है। इसकी स्ट्रिंग क्या हो सकती है आपकी? इसकी स्ट्रिंग क्या हो सकती है? इसको यदि एक्सपेंड करें हम, A प्लस बी को यदि हम एक्सपेंड करें, A प्लस बी को हम, और ये आपका क्लीन क्लोजर, तो इसमें क्या क्या स्ट्रिंग हो सकती है? इसमें नल हो सकता है, यानी एप्सिलॉन हो सकती है ना, है ना। दूसरा क्या हो सकता है? ए हो सकता है, बी हो सकता है, ए डबल बी कुछ भी हो सकता है ना। तो ये इस तरीके से आपका कुछ भी हो सकता है। अब इसका मीनिंग ये है कि क्यू नॉट बी स्टार्ट फ्रॉम द इनिशियल स्टेट क्यू नॉट एंड टेक द इनपुट ए एंड देन वी have a choice. It can be it can be epsilon. So we simply pass the a here to b, simply take the input a and b take the epsilon from here. So we not take the input a and b. So a and b is also accepted by here. And if we take the input from here a comma b, तो a यहाँ से ले सकते हैं आप, ए ले सकते हैं, बी ले सकते हैं. So we can also reduce this epsilon into the this NFA. So here the epsilon, and this is the epsilon NFA for the given regular expression, and this is the NFA for the given regular expression. Now the other topic that we discuss here, the closure property of the regular language. So the regular language are closed under the, first is that complement, second is the concatenation, third is union, fourth is intersection, fifth is difference, uh, sixth is reverse, and clean closure, homomorphism, and inverse homomorphism. This is the under the closed regular expression. So first is complement, second is concatenation, third is union, fourth is intersection, fifth is reverse, difference, clean closure, homomorphism, 6, 7, 8, and inverse homomorphism, that is 9. So we discuss one by one. The complement, if L is a regular language, then L complement. First we describe the complement. If L is a regular language, then L dash is also a regular language. Here this is the proof, like DL Q set of states, input alphabet, transition Q naught, and F is the final state that accept the L. Then we can construct the DFA in the form of reverse Q sigma delta Q naught, and the final state is सेट ऑफ स्टेट में फाइनल स्टेट को रिमूव कर देंगे, हटा देंगे, तो वो आपकी क्या हो जाएगी, रिमेनिंग स्टेट क्या हो जाएंगी, आपकी फाइनल स्टेट हो जाएंगी, है ना. फाइनल स्टेट को सेट ऑफ स्टेट में हटा देंगे, दैट एक्सेप्ट द आल्सो द L dash, make the final state non final state and vice versa. It means that here make the final state non final state and vice versa. So this is the complement. Now now the second property is that concatenation. If L L1 and L2 are regular language, then L1 dot L2 is also a regular language. The proof is that can be represented here. Suppose L1 and L2 are two regular languages, then concatenation of that L1 and L2 can be represented here, and the construct L1 dot as follows. ये आपका L1 है और ये आपका L2 है. मेक इट, इसको हम नॉन फाइनल स्टेट बनाएंगे फर्स्ट वाले को, और यहाँ पे एप्सिलॉन देके और इसको क्या करें, L2 को फाइनल स्टेट बना देंगे. And the next property is that union. The union, if L1 and L2 are regular language, then L1 union L2 is also a regular language. It can be diagrammatically represented here. Construct NFA for the N1 union L2 as follows. So in a state from the here, start from the initial state and epsilon from here and here. So it can be diagrammatically can be write as follows for the union property. So now we write the intersection. Write the regular expression. Suppose L1 and L2 are regular language, then L1 intersection L2 is also a regular language. So can be suppose De Morgan law L1 intersection L2, the L1 union L2, और ये आपका ये dash लगा दिया है, and L2 are the regular, and L1 dash and L2 are the regular, and L1 dash union L2 dash is a regular, और ये आपका complement L1 complement union L2 complement का whole complement is a regular, and L1 intersection L2 is a regular. Now the next property is the reverse. If L is a regular language, then L to the power R, यानी कि L का reverse is also a regular language. Proof can be right here. The construct NFA for the L reverse as follows. Reverse all the transition. जो भी ट्रांजिशन होंगे उनको आप क्या करेंगे, रिवर्स कर देंगे. सपोज दिस. So the transition can be write as here initial final को initial, and make the initial state final state and final state initial state. So is this is simply the reverse. So the reverse is also the regular language. Now if now the next property is the difference. If L1 and L2 are regular language, then L1 difference L2 is also a regular. The proof L1 difference L2, L1 intersection L2 का complement, L1 complement and union L2 complement का whole complement, and L1 L2 are regular, and L1 dash is a regular, and L1 complement union L2 का whole complement is also a regular language. So it can difference also under the regular language. Now we discuss about the next property, that is a clean closure. Suppose L1 is a regular language, then clean closure of L is also a regular language. Proof construct NFA for L as follows. L star follows. Epsilon for that, and epsilon, and then the language, and then epsilon also here. Now the next topic is decision property of a regular language. Now the next topic is what? Next topic is the decision property of the regular language. So we discuss about the one by one. These are the decision property. First, the emptiness, finiteness, membership, and equality. Now discuss one by one. Polling properties are decidable for finite automata. The following properties are decidable for the finite automata. First is the emptiness. To determine whether finite automata accept any language or not. Suppose any finite automata that accept or not accept, it can be determined. So the next property, that is then finiteness. Finite means to determine whether language accepted by finite automata is finite or infinite. Next property, that is membership. So what is the meaning of membership? To determine whether string W is accepted by finite automata or not. It can be defined as a membership. Now the fourth property, that is equality. What is the meaning of equality? To determine whether two finite automata are accepting the same language. If the suppose L1 and L2 are finite automata and then accept the same language, so it can be write as a equal. This is the detailed description of the decision property of the regular language. So we discuss about the one by one. First is that the emptiness. So how to define or evaluate the emptiness? The first step is that remove the unreachable state. Suppose here Q1 and Q2 and Q2 is simply the final state and Q1 is initial state, and Q3 is also a state, that is Q3, this is that. So here we see Q3 is a unreachable state. Unreachable state meaning that we cannot reach at the Q2, that is final state, from the initial state. So here we see it can be the remove the unreachable state. So here we can remove this state if the resulting machine containing at least one final state. इसमें कम से कम हमारे पास क्या होना चाहिए, एक फाइनल स्टेट. तो अपने पास क्या है, एक फाइनल स्टेट है. मान लीजिए ये अपने पास Q2 फाइनल स्टेट है. Step 3, if there is a no final state, then finite automata accept the empty. अब इसमें यदि इसमें कोई फाइनल स्टेट नहीं होती, सपोज Q2 not in the present here, so it is a accept the empty language. So this is the property of emptiness. Now we discuss the next property, that is finiteness. So how to evaluate that finiteness property? So step first, remove unreachable state. Suppose Q1 again, suppose Q1, Q2 and Q3. This Q2 is the final state, this and this. Q1 is the initial state. So remove the unreachable. So Q3 is in removal, Q3 unreachable state. So we can remove here Q3 state. Step 2, remove the dead state. This is also the dead state. So it also remove. Q3, if the resulting machine containing loop or cycle. suppose here the loop, this is the loop, then finite automata accept the infinite language. So this automata accept the infinite automata if their resulting machine do not contain the loop or cycle, then the finite automata accept the finite language. So if there is a no self loop, so Q1 and Q2 and simply accept that. So this is the finite language that accept the finite language. So this is the finiteness. Now the discuss the next property, that is membership. That is 3 property. Let M is a finite automata that accepts some string over an alphabet. Let W is a string defined over the alphabet. If there exists a transition path in M, suppose Q1, Q2, Q3. Suppose W is a string, that is mean A, simply this is the string A and B. This is the string W. Is the string defined over the alphabet. If there exists a transition path in M, suppose this is M in a machine path in which start at the initial state and the end in any of the final state, then string W is a membership of M. Otherwise not a. Suppose W is string that is A and B, and it is a membership of the machine M or not. So it is the member of the machine M because we start at the state Q1, that is initial state, and take the input A and reach the state Q2 and again input V and take the input B, we reach the final state. So A, B is the membership of the language M. So this is the membership property, and then next is properties that equality. Equality to finite, how to define the equality to finite state automata M1 and M2 is said to be equal if and only if they accept the same language. Suppose M1 M2 टू फाइनाइट ऑटोमेटा है और उन्होंने क्या किया, सेम लैंग्वेज को एक्सेप्ट कर लिया, minimize the finite automata and the minimal DFA will be unique. So M1 M2 टू ऑटोमेटा है और वो एक्सेप्ट करते हैं किसी सेम लैंग्वेज को, so it can be treated as a equal machine of finite automata. So here we stop the class here. Now the reference of this class, that is the references KLP Mishra, Motwani and Peter Lenz, also the references of this class. So this is the references.